Okay, so the first talk today is by Andrew Swan from Carnegie Mellon University, and he will be telling us why cubical sets are different to simplicial sets. Go ahead.
Right, okay. So this is about cubical sets and simplicial sets and why they're different. But I'm just going to start by motivating the problem a bit. So like why I was interested in this question. So I guess this kind of starts with what I would call like classical homotopy theory. So the kind of thing that might have been studied by Kahn or Quillen from several decades ago. And the kind of standard thing to do in that setting is to work with a pre-sheaf topos called simplicial sets. So this is a pre-sheaves on a certain category called the simplex category. And inside cubical sets, we can define an important class of maps called Kahn fibrations. And so I guess I won't go into too much detail about why this is an important class, but since this is a type theory workshop, I kind of maybe mention that the reason that we're interested in them in type theory is because they're used to model dependent types. So when we have the simplicial set model or the cubical set model of type theory, these Kahn fibrations are used for the dependent types. Okay, and so the kind of classical definition of Kahn fibration is in terms of a certain it's in terms of the right lifting property against a certain set of maps. So again, I won't give a detailed definition, but I just point out that we have this set of maps which are indexed by a pair of natural numbers k and n, and this delta n, this is one of the representables in simplicial sets, and then this is just a sub-object of the representables called a Horn inclusion. Okay, so a Kahn fibration, by definition, well, by one of the definitions, has the right lifting property against Horn inclusions. So this says whenever we have a commutative square like this with our map F here on the right and a Horn inclusion here on the left, and these form a commutative square, then there is a diagonal map which is dotted in this diagram, which splits the commutative square up into two commutative triangles. Okay, so that's one definition of Kahn fibration and probably the most standard one, but there's several others. And so here's one other definition of Kahn fibration, which is in kind of classical homotopy theory, this is equivalent. And in this case, again, this is defined using lifting properties. So it's saying it has the right lifting property against a certain class. But this time, well, okay, so in simplicial sets, we have an interval object. So an interval object is just a object I, and then a pair of maps to the from the terminal object into the interval, into the underlying object of the interval. And in simplicial sets, we just take this to be a representable. So we just call this delta 1. So it's well, it's not important. It's a representable in simplicial sets, and we use this as an interval object. Okay, and then if we have two maps, we can combine them together using an operation called pushout product. So I think this is originally due to Joyal, but not quite sure about the history there. But in any case, we can we say that F is a Kahn fibration if it has the right lifting property against a pushout product of every map belonging to a class of monomorphisms that we call cofibrations, and the two endpoint inclusions. Okay, and so this is another way of defining Kahn fibrations, and they're equivalent in the sense that they give the same class of maps when we assume the law of excluding middle. but even though the equivalent in classical homotopy theory, they're kind of different from the kind of perspective that I'm interested in. So kind of type theory and constructive mathematics and constructive models of type theory. Okay, so there's kind of two ways that these definitions are different. And one way they're different is that there's a constructivity thing. So although there's these proofs that they give the same class of maps, these aren't constructive proofs. So you need to use the law of excluded middle to show that those two definitions that I gave are equivalent, that they give the same class of maps. Okay, so that's one way they're different. And as well as being constructively different, that they're what I'm going to call algebraically different. And okay, what I mean by this is that when I defined them a minute ago, I said they were defining the class of maps. If these diagonal maps here, I'm calling diagonal fillers, if they merely exist. But what if instead of asking for maps of the property that there exists a map, what if we say, if we treat this as structure instead, and say a Kahn fibration structure is a choice of diagonal filler for every Horn inclusion and every commutative square like this. Okay, so this is the same kind of idea, but just treating it as a structure rather than property. And similarly, we can treat this definition here also as structure. So we can say that it's a choice. So for every cofibration and for each of the two endpoint inclusions, and for every commutative square, we have a choice of diagonal filler, making two commutative triangles, and there's also a kind of coherence condition as well that I won't kind of go into. But the point is, this is a kind of structure, and it's a different structure to the one using Horn inclusions. So this is what I mean when I say that these two definitions are kind of algebraically different, because the structures that they give are different.
Andrew, just quick comment. And in the previous diagram, I think the delta n should be B cross I.
Oh, yes, you're right. Thank you. Yeah. Okay, yeah, so as I was mentioning, these are used in type theory. So the kind of classic model of type theory in using these kind of homotopical ideas is Vygotsky's interpretation of homotopy type theory in simplicial sets. So this is kind of the original model of homotopy type theory, if you like. And this is non-constructive, so it's using the law of excluded middle and the axiom of choice. And these Kahn fibrations, as I said, these are used as the dependent types in the model. Okay, and and so later on, we had so Thierry Cocand and his collaborators come up with, and various other people as well, kind of independently came up with constructive models of homotopy type theory, and these are all based on cubical sets. Yeah, so I guess there's more than one of these, but here I was talking about the what I'm going to call the CCHM cubical set model. So this is Cohen, Cocand, Huber, and Wartburg. Here they define a notion of Kahn fibration structure, and we can think of this as like based on the pushout product definition of Kahn fibration, and it's not in simplicial sets, but instead it's in a different pre-sheaf category called cubical sets. Okay, and so this is kind of one way to get a constructive model of homotopy type theory, and it's also possible to do constructive homotopy theory. And in this case, we can use, so this is due to Simon Henry, Nicola Gambino, Christian Sattler, and Carol Samillo. And they kind of developed something which is kind of closer in spirit to classical homotopy theory, but done in constructive mathematics. And so in particular, that they use simplicial sets, just like just like Kahn and Quillen and all those people did. And I think it's kind of still open if you can get a model of type theory this way, but there's a lot of stuff they can do. And in particular, they showed they can get a model structure, something called a model structure on simplicial sets. And they kind of work towards an interpretation of type theory. So in particular, they have a univalent universe in a certain sense. They can also they also have some work on dependent products as well. So there's a sense in which this model structure is right proper. But yeah, I won't go into any more detail about that for today. Okay. So it's kind of natural to ask why. So if simplicial sets are working so well in classical homotopy theory, I think it's natural to ask, why did we have to switch to cubical sets for constructive models of homotopy type theory? So I'm going to kind of break this down into two parts. So why couldn't in CCHM cubical sets, why couldn't they use the Horn inclusion definition of Kahn fibration? And okay, maybe once we've answered this question, maybe they do have to use the pushout product definition. But in that case, if they have to use the pushout product condition, pushout product definition, this makes perfect sense in simplicial sets, and is even one of the kind of classical ways to characterize Kahn fibration. So why couldn't they use simplicial sets instead of cubical sets? Okay. Right. So the first part. So for the first question, is the answer is dependent products, and yeah, and so I guess this is already true for a slightly earlier cubical set model by Besam, Kokand, and Huber, and they kind of one of the motivations for the way they define Kahn fibration is to make sure that the Kahn fibrations are closed under dependent products. And so of course, that they use this to make sure that dependent products are working okay in the model of type theory. So that's kind of their motivation. And in fact, there's this kind of counterexample by Besam, Kokand, and Palmgren, who showed that if we use this kind of Horn inclusion definition of Kahn fibration for simplicial sets, then the Kahn fibrations are not closed under dependent products. And just to kind of illustrate this, there's a kind of simpler fact which is kind of related, and this is the closure of fibrant objects under under exponentiation. Okay, so yeah, so we say that an object is fibrant if the unique map to the terminal object is a fibration. And then we note that this satisfies a Horn inclusion definition of fibration if and only if this kind of canonical map from the Hom sets from delta n to x to the Hom sets from this Horn to x has a section. So like a map going the other way around, a section. And and kind of by analogy with the what happens in the two definitions of Kahn fibration, we could instead replace these Hom sets with exponential objects. So yeah, so here we're replacing Hom from delta n to x with the exponential delta n to x, and then we could instead ask for a section of that instead. Okay, and then so this is kind of a stronger definition of Kahn fibration, and then the idea is that these ones are not preserved by exponentiation, but the strongly fibrant ones are. So just kind of maybe quickly sketch a proof of this. So we're assuming that X is strongly fibrant. So we're assuming that this canonical map, each of these canonical maps from X to the delta n to X to the horn has a section. And then we want to construct the same thing for X to the Y. So we have X to the Y, delta n to X to the Y, to lambda and K. And then so we need a section of this, and then kind of constructing a section kind of very roughly is the same as constructing a map delta n times X to the Y to the K and K horn to X to the Y. And yeah, and then so this is the same as again. So this is, but both times I'm applying the adjunction between the exponentiation and products. So this will be y delta n times yeah, times X to the Y and then K to X. Okay, but then we notice that this guy is isomorphic to, well, we can just swap around the exponentials, and this kind of tells us what to do. So we can first evaluate this y and this exponential to get a map delta n times X to the mk horn, and then we can apply the section here, fibration structure on X, to get a map into X, which is kind of what we need. And so that's how the section is constructed. And we can see that this makes a sensible use of the fact that we're working with exponentials rather than Hom sets. And you just have to kind of trust me that, in fact, for Hom sets, they're not closed under exponentials. So in fact, I think this was even proved in the paper that I mentioned by Bezam, Kokand, and Palmgren. They gave a quick-way model where it fails. Okay. Okay, so now for the second question, which is, why can't we just use this push-out product definition of current fibration, but use it with simplicial sets? And in fact, we can, almost everything works, and the only thing which doesn't work is the universe, which classifies small current fibrations. So these are used in type theory, in the model of type theory, to interpret the universe of small types. And yeah, and then so what we notice is that in both cubical sets and simplicial sets, there's not only a univariant universe, but there's a very well-behaved universe. And it's very well-behaved in the sense that, okay, well, we're working in a pre-sheaf category, so we have a kind of a Hoffman-Streiter universe for classifying small maps. And so I call this V, and well, so the map is V dot to V. And then we have a map from U to V, and fibration structures on a small map from X to Y correspond precisely to factorizations of this map to Y through U. So this U is, so once we have a small map and we've characterized it as a classifying map of a map into V, then the fibration structures on our map F yeah, so F is a map from X to Y, so this is F, correspond precisely to factorizations through U. So this is a very nice kind of classification property of the universe. Okay, and oh yeah, in particular, U itself has a can't fill in operation, which is just kind of corresponding to the identity on U. This kind of holds in some generality. And so there's this kind of fairly general result by Licata, Orton, Pitts, and Spitters. And there's a kind of a later alternative version of this by Steve Aldi. And they showed that if the interval appearing in the definition is tiny in the kind of internal sense, which says that this this exponential function has a right adjoint, then the universe, well, essentially what they showed is, yeah, you can show that the universe has this kind of nice classification property. And then so in this paper, they observed that their proof does not apply to simplicial sets because the interval is not tiny in this kind of strong internal sense. Okay, but you might say, okay, maybe if this proof doesn't work, maybe there's like another proof that we can use instead, and use this to get kind of a nice universe in simplicial sets, which satisfy this kind of push-out product definition of Kahn fibration. And so the new result is that no, we can't do this. And yeah, and okay, and I guess I should maybe go through this quite quickly now, but so I just go over the main ideas. And first main idea is kind of idea by Shulman, Mike Shulman, who kind of showed that this nice property of the universe is not really about universes at all. It's actually a kind of inherent property of the structure. And so he kind of defined structures using what he calls a notion of fiber structure. So this is a discrete fibration on the wide subcategory of the arrow category on C, where instead of all commutative squares as morphisms, we just have the pullback squares. And then we say that this notion of fiber structure is locally representable if it has a right adjoint as a functor. So it's a discrete fibration, so in particular it has an underlying functor, and it's locally representable if this is a right adjoint, and equivalently it's comonadic. And also there's another characterization in terms of representability. Okay, and so the theorem is that this fails for simplicial sets with the push-out product definition of Kahn fibration, and for like various other ones. Yeah, so I won't define these, but I just kind of maybe talk about the main ideas which go into the proof. And so one key idea is that if a notion of fiber structure is locally representable, then by comonadicity, the underlying functor creates colimits. So if we look at the special case of the colimit of pushouts and say, expand out what this means, this is saying that if you have a cube like this, where the sides are all pullbacks and the top and bottom are pushouts, and if we're given fibration structures on these three maps, then we can paste them together in a unique way to get a fibration structure on this map. So that's just what it means to create pushouts for this this functor. And so this is what fails for simplicial sets for the fibration structures that I gave. And yeah, and so I don't think I have time to like go over the proof, but I just say that the kind of key point why this applies to simplicial sets and not cubical sets is that the interval object has a linear order in the internal language of simplicial sets. And so in fact, this is a kind of characterization of simplicial sets, if you like, the classifying topos for intervals with linear ordering. And then so this can be used to construct a counterexample in the internal language of simplicial sets. And the thing that actually gets contradicted is the uniqueness. So I construct a pushout like this, but with two different fibration structures. So it contradicts the uniqueness part of this lemma. Okay, so that's the kind of rough idea how it works, but I just skip over these details. And yeah, so just in summary, in CCHM, they use a pushout product definition of current fibration because that's how they got the dependent products to work. And then in order for this to be locally representable, you have to use cubical sets rather than simplicial sets. And we could use the Horn inclusion definition of current fibration to get a well-behaved universe in simplicial sets. And this is kind of what Nicola Gambino and Simon Henry and those guys do, but they it's kind of still open, I think, whether you get a model of type theory that way. So and hopefully this will appear in a paper soon. It's almost finished written up. So thank you for your attention.
Great, thanks very much, Andrew. We'll do our usual silent visual applause. Someone could ask a question, but while we're doing that, we'll get the next speaker lined up, Jonathan. So if you could stop sharing, Andrew, and if anyone has a question, please just unmute yourself.